So hello everyone, thank you to be here for this third session. Today we will finish the chapter 2 on the measurement problem. So I know there are people in the room or maybe on Zoom who couldn't attend last session, so I will just start with a short recap on, because otherwise you will not understand anything. And today, so I hope we will have time to go through all 6 main interpretations after having satisfactorily, hopefully, define the measurement problem. So last time, remember, we went through a history of the measurement problem. By the way, erratum here, I draw a very long timeline of the important dates, historical dates of the measurement problem, and I said, surprisingly, I couldn't find anything between 1982 and 2020, and I didn't want to, shock anyone or disappoint anyone, but in fact, I have found an important date that deserves to be here, the 1996, so Arroche experiments. So experimental confirmation of decoherence. Well, it's much wider than this, and in fact, this experiment has a lot of impacts on many aspects, but at least in the current topic for decoherence theory, important date. So remember last time we investigated or let's say reviewed all the main ways people define the measurement problem in the literature. And I said, remember, I said it's a mess. There are so many different ways, and I managed to divide them in 3 main categories, and I showed point by point why none of them are satisfactory. And in particular, a major drawback was that the definition given for the measurement problem is generally very rooted in the old school textbook standard presentation of quantum mechanics. But even more importantly, it's generally interpretation dependent. Meaning, for example, when people define the measurement problem as the conflict between unitary involution and collapse, well, it's meaningless for at least 4 out of 6 of the main interpretation written here on the board, because for 4 out of 6 of these interpretations, there is not even a notion of collapse. So defining the measurement problem with this notion of collapse cannot be a good definition. It might be the manifestation of the measurement problem in some way, in some Copenhagen-ish interpretation, which I would rather call the textbook standard interpretation, which is, I mean, not as refined as Neo-Copenhagen could be. Anyway, so to propose an interpretation independent definition of the measurement problem, I said the strategy is to do just like Bell's theorem, or all the no-go theorem we'll study in chapter 3 next week, namely to ground everything on the empirical statistics and nothing more, and just say something at the level of the statistics, and highlights a property of the empirical statistics that we observe in some experiments, namely the quantum experiments, namely the interference experiment. Highlight a property that is violated in these experiments, which is not me interpreting anything, which is just empirical facts, empirical statistics, and then translate this property of the statistics into some philosophical meanings, right? So we stopped here. So this is a recap of the last board of last time. I introduced something called I called the TPF, for total probability formula, which is just this. And I said this, well, it's just a trivial consequence of the 𝗁𝗂𝗺𝗿 axiom, right? So it's the trivial consequence of sigma additivity. But I could just, each time I say TPF, you can just understand sigma additivity, but I prefer to emphasize on this formula more, because you will see it's easier to give it some philosophical meaning. And I said, and I also introduced this. So last time I called it property O, erratum. I will rename it property EI, because I will use it a lot in the next chapter, and I think it's a bit more precise. So O was standing for objectivity, but this word, is very heavily loaded in the philosophical literature. So let's call it epistemic ignorance. And it connects very well with the history. You remember when I said statistical physics is the beginning of epistemic ignorance. Before that, it was full knowledge, etc. So epistemic ignorance, which I called before O, is this property. Even though the actual value of a variable is not known, it still has definite value among the possible ones. This, I call it epistemic ignorance because I could, in a more concise way, but less understandable maybe, I could say it equally means all ignorance is epistemic. And the big claim is so this philosophical principle, this metaphysical principle, I claim that I can translate it into math, into the properties of the statistics as the TPF. And I argued why decoherence, for example, is the process after which the TPF is approximately at least satisfied in some basis, and that coherence, so the main, for example, resource used by quantum computers to do some non-classical tasks, etc., is precisely the ability for a system to deviate from the TPF. And now, the fact, the empirical fact, forget about quantum mechanics. Just think a second, just in terms of how is the universe in which we live. We live in a universe in which the TPF is not fundamentally true, in which it is violated. Think of the double slit experiment again. So you cannot have, the probability of finding an electron here on the screen is not the sum of the probability of finding the electron at this location, given that it was on the left, plus the same thing with right. You cannot condition on an event, namely here the event, the which slit information. So empirical fact, we live in a universe in which the TPF is not true. But because the TPF is the translation of this, we have to reject EI. And I say this is the measurement problem. And this is an interpretation-independent formulation of the measurement problem. Maybe for now, maybe you will find it a little bit weird, this process of writing down a metaphysical principle, translating it into math, invoking an experiment and saying, oh, this is rejected, so we have to violate the principle. But keep this in mind, because chapter 3 will be only based on this, when we will study all the the major no-go theorems of quantum theory. Associated to quantum theory, in particular Bell theorem, but many others. The method will be always the same. Metaphysical principle or principles, translation into math, an experiment that shows that this signature is violated, and then we have to reject the metaphysical principle. Good.
Can I ask a question?
Yeah, please. Yeah, so I didn't write it down because last time, so I said it orally. Last time I introduced it. So TPF stands for, so this formula, total probability formula. So there are many ways to name this formula. Some people call it the sum rule, or some people call it the law of total probability, but I prefer this because it's neither a law nor a rule. It's just a trivial consequence of sigma additivity.
Sorry, but for the epistemic ignorance sake, that they may be,
even though the actual value of a variable is not known.
Okay, so if there is a definite value, then there must be an hidden variable that follows its evolution.
If you want, in some sense, yes.
Because it exists, it has definite value.
If you want, yeah, in some sense. It depends on what you call a hidden variable, but yeah, it's related to this. And by the way, precisely, ask your question and then. Yeah. We know, and in fact, what I'm claiming here is that we don't even need Bell theorem. We just a double slit is. This is what I'm doing here is a zero step or no-go theorem for the dummies. Like zero no-go theorem, we have a claim, a metaphysical principle, we translate it into math, we observe an experiment violating it, so we reject. And Bell's theorem is doing the same, but it's more complicated. And so that's why I was saying, keep this method in mind because we have the same. And just a remark, a hidden variable is often, when you want to define what is a hidden variable, it's generally, you know, so a variable lambda living in some set with some probability distribution which is basically unknown, but with the fundamental property that you have a TPF, or I should write it this way, that you have a TPF when conditioning on the hidden variable, which means that which grasps this notion of objectivity of the hidden variable. And I will give many other examples to show you that the TPF is ubiquitous in the quantum foundation literature, although often unnoticed. Yeah, there was another question or no? Okay. So this is all good. This is an interpretation independent formulation of the measurement problem. But we want to you know, derive or maybe reformulate this philosophically to see the consequence of this, because for now it may seem a little bit abstract. So I will write down a lot of equivalent reformulation of how I understand this, the rejection of EI. Absence of, I would say, objective ontology for quantum matter. But so objectivity, everyone has this notion, you know, intuitive notion of objectivity, but the problem is it's a bit too intuitive, and also it's as I said, it's a very heavy loaded word in philosophy. So let's try other reformulation escaping this word objectivity. So the absence of ontology, independence of epistemology. The measurement problem is the absence of ontology independent of epistemology. Because I have to reject this, and you know, here that there is the known, to be known. So this notion of, you know, being dependent or not on epistemology. Some expression that I like, I will use them a lot. The absence of what I like to call a third person point of view, or I would say, or third person, or I could say godlike point of view. And sorry,
Nature.
yeah, why not? Yeah. So again, so now, yeah, I am doing some philosophy here, so it's not just math. I cannot define any words I'm using. But so when we do philosophy, what do? You write texts and you create a framework, a net of words and a network of meanings that, you know, is self-sufficient. So that's why I'm trying a lot of reformulation to give you an intuition, and then we can debate and maybe we will agree and believe that we think the same thing, or that way you have grasped at least the idea I'm trying to convey. Another way is, this is an expression very fashionable at the moment in philosophy, the view from nowhere. Have you heard of that? There is a French philosopher, philosophy of ecology, whom I love, Bruno Latour, who uses that a lot. He defines himself as an anthropologist of science, and I think this definition suits him very well. The view from nowhere. Maybe from, yeah, from, yeah. View from nowhere, yeah. Yeah, sure. And this is an expression from Czeslaw, Indiana. external view. So I will use these as synonyms, and I hope that we have more or less the same meaning in mind when we use that. But it means that, you know, you cannot at the same time write down and know everything and write down a point of view which encompasses everything in the world. A little quote by 𝗰𝗵𝗽𝗁𝗁. So from a recent paper by 𝗰𝗵𝗽𝗁𝗁 2022, I strongly suspect that the ultimate message of quantum mechanics, I know it by heart, this one. I wrote it so many times, but I checked to be really sure, is that the separation between what exists and what is known to exist. So the epistemic. So by the way, he wrote the epistemic and the ontic, but it's much more sensible to write it the ontic and the epistemic. Must be abolished. Now, let's go further. So, I emphasize the TPF, but again, the TPF is just, I mean, equivalent to sigma additivity. And so it's just a way to highlight one aspect of the Kolmogorov axioms. But more generally, I argue that the Kolmogorov axioms are the axioms of epistemic ignorance. Right. The Kolmogorov are the axioms of epistemic ignorance, and everything you can consistently model with a Kolmogorovian theory is, by definition, if you want, is the kind of definition of epistemic ignorance, is something that contains only epistemic ignorance and not ontic ignorance. So it's with underlying objectivity, if you want to keep with this word of objectivity, but I will try to use it less and less during this course. And now, consequence. Now, this is a cute reformulation. Again, I'm just saying the same thing all the time, but cute reformulation. The measurement problem is the existence of ontic ignorance. And this one, I box it. Namely, the impossibility to describe the universe with a Kolmogorovian theory, at least in some regime. At least you can in some regime, in the classical regime, but you cannot on any experiment that humans have been able to perform. So the impossibility to describe with a Kolmogorovian theory. the measurement problem is the existence of ontic ignorance. So a remark orally, because it will be quite technical, and I'm not sure many people in the room can understand, but maybe some of them can, and at least for the recording. So just to argue that the TPF is, as I said before, ubiquitous in the quantum foundation literature, although often unnoticed or not emphasized sufficiently, according to me. So just a list of examples of where you find the TPF. So I wrote down before the very definition of a hidden variable is a TPF. And if you look at Bell's seminal paper 1964, but also in the later ones, typically 1981 and so on, you find in the very beginning of the paper some beautiful TPF, although it's not written down this way. And also there are some modern reformulation of Bell's theorem in terms of causal model. It's very fashionable at the moment, typically Wood and Speckens. And you can find in the very introduction of the paper again some TPF that tries to encapsulate this notion of objectivity. And now the good framework today to deal with hidden variable and non-contextuality is something called ontological models designed by Speckens mostly. And definition one of Harrigan and Speckens' seminal paper on ontological model is a TPF. Now you have another important no-go theorem that we will study next time, Leggettgard inequality. The macro-realism assumption is a TPF, as we will see next time. In the local friendliness theorem, so I announced it, for me it's one of the main last result obtained in quantum foundations on the measurement problem. Absoluteness of observed events, it's an assumption, just like epistemic ignorance, but just similar, is a TPF, among other things. Or decoherent histories, so this is an approach by Griffith and Hartle, I think also. Well, I will not dwell on that, but you have a functional, the decoherence functional, which is designed to measure a deviation from the TPF, in essence. So it was just to argue that this object is present everywhere. Now, so why do we struggle so much with the measurement problem? It's been a century of controversy. So the godlike point of view have proved extremely successful up to the 20th century in science, in modern science. Yeah. So the ontology of Newtonian physics is a godlike point of view. The Newtonian space-time, you can't imagine more, godlike view from nowhere. You grasp the single universe at once, and all the particles also. You can write down their position and trajectories everywhere. It's a view encompassing everything. It's not a partial view.
But it is possible, at least in principle, to know everything.
Yes. Yeah. There is. So all ignorance is epistemic, meaning that there is a state of affair behind. Maybe you don't know, but
someone knows.
Yeah, God knows. Yeah, God exists and has a point of view. So I'm trying to kill God. Yeah. So to make it revive. So a century of controversy. On the measurement problem, because of our reluctance to abandon the idea of an objective world, right? Or the objective ontology. Question mark. I'm not 100% sure. Yeah, today will be the most controversial session, of course, because we are really into the philosophy of the measurement problem. So I cannot even pretend I'm doing something objective, right? Now, if you say so, if you agree with that, then is the measurement problem really a problem? I mean, isn't it just a problem for the people who just are too attached to this view from nowhere? So do we care after all about the measurement problem? Is the measurement problem just or only a problem for those too attached to the view from nowhere? But if so, I can just say, well, no, I'm not attached to this. Okay, I let go with objectivity, and then why do we care about the measurement problem, right? You can just let it go. No. We have to consider it for at least two reasons, because there are at least two things to clarify. No. Two things for an explanation. One, we need to explain the apparent objective world, because, okay, it's easy to say, okay, I let go with objectivity. I don't believe in that, so I'm not surprised with the measurement problem. Right, but okay, but today, in everyday life, there is a very strong impression of objectivity, and it's easy to say, well, no, I don't care about objectivity, but I mean, humans never, as far as I know, question the universal validity of the TPF. It was a tremendous event the first time we measured it experimentally, and intuitively everyone is equipped with this deeper sense of objectivity. So it's easy to say I let go with it, but you have to explain why humans are so deeply believing in that, and if they are so deeply believing in that, it's because the world seems very strongly to believe objectively. So we need to explain the apparent objective world in a quantum universe. And this is the task of the quantum to classical transition, one of the greatest, most magnificent part of quantum foundations. I will not give a course on it because I don't have time, but next week, no, Tuesday afternoon, informally, we do a little seminar discussion. I will show a few things, but it's not as standard and established as what I'm showing today. So this is the task of the quantum to classical transition, a huge literature that started already in the 20s, 30s, and which is far to be settled. The problem is far to be settled. Two, well, even if you have that, I claim that it's easy to say, oh, let go with objectivity, I don't care. But at least if you are really interested in being able to explain or being able to have an understanding of quantum mechanics, then you need to build a metaphysical picture, right? Or at least to be to be relaxed with yourself. We need or you can embrace the shut up and calculate attitude, which many people do, but I argue it's fleeing in face of the problem. Metaphysical picture consistent with what we know of the world. In particular, the violation of the TPF. In particular, so you need an ontology consistent with that. Now, a lot of remarks. So remark 1. This one will be, why is classical optics a wave theory? So too often, people seem to think, to hint at the fact that, well, you have classical optics and it's just, you know, it behaves linearly because it's the theory saying so, and it has nothing to do with quantum mechanics. But I don't agree. Classical optics is just an emergent consequence of quantum mechanics, and the reason why photons, like what you can learn in what you teach to your students, so you know, sorry, yeah, classical electromagnetism, or you know, the classical Young experiments, for example, or diffraction, all Snell-Descartes laws, everything, you know, classical optics. Why is it a wave theory? In fact, in the end, it's photons. We know that today, and photons behave quantumly. But classical optics is obtained as a limit using the law of large numbers of experiment with a single photon. Why? Because photons, they are not charged, so they barely not interact. They don't interact with each other, in fact, and they are not charged, and they are bosons, so you know they don't see each other at all, and they don't decohere themselves. Therefore, a classical optics experiment is best seen as just a huge number of single photon experiments in parallel, and you average using the law of large number. You will obtain definite results, and you wash out the probabilistic aspect of the theory. So photons are bosons not charged, they don't interact. And they don't decohere. Maybe you don't know what is decoherence yet, but if I come back in spring, I can give a new course on decoherence, and I thought I would have time, but don't decohere each other. Therefore, an optics experiment is best seen as many single photon experiments in parallel plus law of large numbers. And now, why is it a wave theory? Because each photon individually violates the TPF. And because it violates the TPF, it means that you cannot, I explained last time that the TPF is, you know, the ability to distinguish between two potentialities, because on exactly one of them is satisfied and not the others, the statistic behave as, you know, independent histories which don't see each other. So the trivial example I gave last time is, imagine I give an exam to my students. Even though I don't know whether my student has worked or not, she is in one of these two cases. And therefore, the probability that my student gets a good mark at my exam is the probability that she gets a good mark given she has worked times the probability she has worked, plus the same thing with hasn't worked. And I can do that because I know that she is in one or the other state. I have a longer argument to explain exactly how you recover the TPF from this assumption. I don't have time today, but the TPF translates the fact that you have in each run exactly one potentiality is realized, and they don't see each other, these potentialities. Conversely, violating the TPF means that you have like a sort of magma of potentialities which all seem to contribute to the statistics. And so here in this case, each photon violates the TPF. Therefore, each photon seem to have statistics involving both potentialities. Right? It seems that, and therefore, it's like a wave behavior. But it doesn't mean the TPF is a wave. It means the TPF violates the TPF, and the consequence of the statistic is that it behaves a bit like we are used to see waves. Each of them violates the TPF behavior like a wave, wave-like behavior. What did you say? Yeah. Wave. Despite not being a wave. No, by the way, today in quantum foundations, literally no one uses anymore this expression wave-like particle duality or wave particle duality or so on. It's a very old-fashioned concept that has made its time, you know. So, remark 2 on Schrödinger's cat. So, the mystery with Schrödinger's cat is not that the cat is alive and dead. It's stupid to say so, because if you open the box, you just see the cat alive or dead, and quantum mechanics predicts very unsurprisingly that if you open the box, you have 50% chance to see the cat alive or dead and nothing more. And so there's literally no mystery on that. So the mystery is alive and dead. If you open the box, or quantum mechanics predicts very unsurprisingly that if you open the box, you have 50% proba to see it alive and 50% to see it dead. Is there anything surprising here? No. But there is, of course, a surprise. But to express it without any abuse requires a very long sentence. So the mystery is that, so if one could measure a non-commuting observable of the cat, So in a basis that is not compatible with the basis alive and dead. So the cat in a basis, remember bases are identified to the question you can ask to a system. Recall the first session. In a basis, complementary to so this is the basis containing alive, dead, and then you complete the basis however you wish, and you must choose another basis complementary to that. Then the observed statistics would not satisfy a TPF if you condition on the cat being alive or dead. That's all you can say. Would not satisfy the TPF on the cat or dead. That's all you can say. So there is still a big mystery, and we will go closer. We will study this more in depth when we go to the next session on Wigner's friend. But I wanted to clarify this first. Now, let's say something about QFT. So again, I will be super provocative as usual, but it's to open the debate, so feel free to react violently if you want. Quantum mechanics versus QFT. Ready? So quantum mechanics is the only non-Lagrangian theory. It's the only theory that is not derived by a delta S equals 0 in fundamental physics, in theoretical physics, right? And there is a good reason for that. Right, fundamental, so I just include, QFT, GR, SR, and QM, right? Special relativity. Yeah. It's the only non-Lagrangian theory not derived from a delta S equals 0. Do you agree with this, at least so far? Okay. Well, you have a Lagrangian in QFT. I mean, it's the central object probably. In GR, it's the same, right?
Yes. Okay.
What is the action? So what is it? I've never seen such an action.
If you want to derive the Schrödinger equation
from an action? So how is the action? I've never seen this action.
It's I h bar psi star psi over dt plus gradient of psi star gradient of psi divided by bar multiplied by.
Okay,
I can show you.
Yeah, I'd like to see that. So again, I'm not 100% sure what I'm going to say here, but still, I want to convey a message. So maybe there is an action, I don't know. I'm very curious to see. But the fact is, we never use it. No quantum mechanics physicist uses this action, and you see, I'm not even aware of the existence.
By definition, if you have a delta S equals 0, you have a classical.
That's where I'm. But QFT is supposed to be a quantum theory, and I'm coming to this.
But in QFT, you don't use delta S equals 0 unless you use the classical. Yes, classical.
Sure, and so it goes exactly in line with what I'm going to say. There is a problem when you try to do a Lagrangian theory, and you could say, yeah, field theory is not quantum field theory, but still we write Lagrangian everywhere in QFT courses, and it's a central object, contrary to quantum mechanics, and so that's what I want to say. um, a Lagrangian is a godlike object, is a view from nowhere. View from nowhere object, yes. Or viewed object, yes, that's good, yeah. A view from nowhere object, or an object view from nowhere. It encompasses everything.
It's not the same for H, for the Hamiltonian. Say that it does not encompass everything.
Good remark. I think about it. Let me finish. Yeah, good remark. Okay, I think it encompasses everything. There are no internal observers in QFT. There are no first-person point of views. Contrary to quantum mechanics, because, well, I don't have time today, but there are many arguments to be convinced that a wave function is a first-person object, and it's just the tools that collects all the statistics, the credences that one agent can formulate about the world. But when you try to when you try to force the wave function to be an objective object common to everyone, you run into billions of problems, especially when you include special relativity. Maybe I have time one day to develop more on that. The Fock space, and so contrary, I will just write that. Contrary to psi, which is a first-person point of view object, and yeah. Well, I should have prepared something to argue more about this, but and therefore the Fock space, so the Hilbert space of QFT, is a desperate attempt of doing something, of forcing psi to do something it is not supposed to be. It is counter nature for it, forcing the Hilbert space to become a third-person point of view object. Is a desperate attempt to save the view from nowhere by forcing psi to be a third-person point of view, a third-person point of view, something it is for which it's counter nature to do that. So something going against its very nature. And people are actively trying in my community to implement properly the notion of measurement in QFT. It's a challenge, a huge challenge, and for now it's not working very well. I mean, there are recent progress. It's a very active topic, but it's super hard. And I think the reason why it's hard is because from the beginning, QFT was supposed to be a theory without any observers. It's a theory of you prepare infinitely in the past something, and you do something in a particle accelerator. QFT, as it is used today, is nothing more than a theory of particle accelerators. That's why people struggle to do more with it, because in principle it could be more. You could have the idea to implement the notion of observer and measurements, but it was not built for that. It was built as a theory of no measurement ever occur except infinitely in the future. And you do one experiment in a particle collider, and you obtain a statistic, and then that's all. And you restart your full history again, and you restart with something infinity in the past, and that's all. And there is no sequence of observed events and so on. And that's so Thierry with like this. Is it the root or the deep cause of Haack's theorem, the need to renormalize, because renormalization, as Thierry told me one day, is perhaps understood intuitively as the need for going into a sort of meta-Hilbert space, because Haack's theorem tells you that you cannot have one and the same Hilbert space describing both the non-interacting and the interacting theory. So renormalization is this trick to escape this Hilbert space and go into a bigger one. And if you, but it's not a surprise, because the Fock space is a counter nature object from the start. Okay, I don't write more. Yeah. Yeah, feel free to ask a question anytime. No, a question or no? Okay. I forgot to say on the first remark, the why is classical-optic wave theory. You know this experiment with polarizers. You know when you send light, you have a polarizer like this, and then a polarizer like this, and you collect here in your detector. And if you do that, you recover zero energy here. But if an experimentalist arrives and adds another object which can only absorb energy, not create, well, you recover more, because you recover something here. Why? Because the TPF is violated. That's all. That's the only reason. Because the TPF is violated by photons. Okay. Why is quantum gravity so hard? So during my PhD, I couldn't sleep because of the measurement problem, but I also couldn't sleep because there is nowhere in the literature a clear explanation of why it's so hard. I mean, why can't you just, add the two theories and you plug the Lagrangian of QFT and you just add, the Lagrangian of Einstein-Hilbert action, and that's all. Why not? And when you try to look at the different approaches, it's hard to understand why they fail, except by people give, technical arguments, mathematical arguments, technical details. So people tell you, well, it's non-renormalizable typically, or they tell you that I don't know. At high energy, QFT should be a CFT, I think, but GR cannot be, or things like that. I've heard a lot of explanation like that. Good. For me, that's an explanation that presupposes the form of the thought theory. I don't know whether quantum gravity should be expressed in terms of fiber bundles of operator of a manifold, should be expressed in terms of normal tools used by particle physicists and renormalization and so on. I don't know that at all. But in my community, it's the same problem. People say try to understand some aspects of the possible quantum gravity theory, and so they do what they can, but so you often have this undefined notion of superposition of space-time. You know, they take superposition of masses and they try to see what should happen under some basic assumption. Reasonable, of course, but I don't know if human will ever be able to build a satisfactory theory for quantum gravity, but I'm ready to bet that if they do, there will be no notion of superposition of space-time. But so maybe I'm wrong, but it means just that it's plausible, and therefore answering to this question by saying something about arguments about superposition of space-time as though, you know, space-time was kept in a Hilbert space. It's not a deep reason. It's interesting, but it cannot be taken as a deep fundamental reason for why QM and GR are so incompatible.
What do you want to reject? Superposition or space-time?
No, the fact that the idea that space-time should be seen as a ket in a Hilbert space, and you can take linear superposition of that. This no, for me it's nonsense. There are many reasons, but it would be too long to develop. But yeah.
But you still agree with superposition?
Yeah, but at the level, but yes. Yeah, but when we say quantizing space-time, first, it's not even clear that we need to do so, and there are very interesting works doing some classic treating space-time classically, matter quantumly, and trying to see what are the only possible mathematical relations that you can have between two such theories. And in fact, it's super constrained. So important names on this approach are Oppenheim and Jonathan Oppenheimer and Antoine Tilloy, for example. Very interesting approaches, although I don't believe a second that spacetime should be semi-classical, but I'm happy that people work in this direction because I might be wrong. Just to say it's not obvious, and that spacetime should be quantized, and even if it should be quantized, the word quantizing is used in dozens of different meanings. And what does it mean? It doesn't necessarily mean a Hilbert space. Doesn't necessarily mean, for me, the only meaning that you can have is violating the TPF. And I am sure that space-time variable, in some sense, should violate the TPF, and you should look for a theory that allows a violation of the TPF in space-time variable. I will develop more on that later. This I'm sure. The rest I'm not sure. Why? Because it's the core aspect of quantum matter, and it's an interpretation independent one, and it's a theory independent one. It's just at the level of the statistics, experimental statistics. It's not me interpreting anything. So,
but what
yeah.
If you cannot do statistics? Because if you mention statistics, it means that you are able to do experiments, that you repeat your experiments.
Yeah.
Well, for space-time, you may not possible.
Yeah. So, but again, I'm giving intimate convictions. I don't have a proof. I'm just, you know, it's the avenue I'm exploring. But I'm very happy that people are exploring other avenues. But why do I think that the violation of the TPF, that we should look for a theory allowing to violate the TPF? Well, I think I will explain this remark, and I think it will answer. So, a universal reason. Yeah, it is. So, as I said, we want a universal reason for the incompatibility of QM and GR, and not relying on just purely mathematical reasons, just like non-renormalizability or whatever.
But when you say non-renormalizability, but purely mathematical, you mean it's just because you are unable to do properly the mathematics and the problem is solved by...
No, but there are deep arguments, as far as I know, for why GR will never be a renormalizable theory, even if you quantize it in the canonical way. Am I wrong?
Yes, sir.
Yeah, there are ways to renormalize it.
But there are, apart from the dimension of the property concept, if because general relativity seems to be renomized. We need to work out to find a counterexample.
Okay. I thought it was claimed as one of the main obstacles, non-renormalizability of QG.
Non-renormalizability of general relativity is interpreted as a fact that there is something happening beyond the cutoff.
So it's non-renormalizable a priori, right?
Yes.
So I thought you were saying the contrary. So
maybe we talk.
Maybe, yeah, but it's very interesting. I like when it's interactive, so don't worry. So let's provide a universal reason. So in short, differential geometry pictures, in essence, a view from nowhere. What is differential geometry? It's like you are God and you see your entire full manifold externally as a third-person point of view, and you see everything, and there is only one manifold. Of course, there are charts, and charts account for the point of view of the observers. So there are first-person point of views, that's okay, but there exists an underlying third person which knows everything and from which you can derive all the first-person point of view.
And this first person knows everything, but does not have an influence.
Maybe not have an influence, but I'm just saying there exists a theory which knows everything, in which you can write everything, you can encompass everything and derive all the first persons. There is one absolute common space-time to everyone. By the way, GR, so I'm coming to this, so yeah, just finish this sentence. An objective notion of space-time, an objective notion of events, common to everyone. By the way, so Einstein's relativity is a very bad name, and Einstein himself didn't like this word at all. He preferred, in a letter he wrote, he would have preferred invariance theory, which is exactly the opposite as relativity, right? And mind this, a possible common phrasing of Einstein's principle of relativity is the laws of physics should take the same form for every observer. But I mean, I should call that the principle of absoluteness, not the principle of relativity, right? You say that there is something common to everyone. And this is why differential geometry was exactly the good framework for that, because it's a view from nowhere. It creates an objective object, one and the same for everyone, the manifold. So Einstein space-time is perfectly absolute, just as absolute as Newton's. Perfectly absolute.
But here,
he preferred invariance theory more than relativity. Because there is something invariant, namely the laws of physics, namely, you know, this way of arranging space-time, common to everyone, the differential geometry was the perfect framework for that. Because you have both a third-person point of view and encapsulating this thing that remains constant for everyone, plus you can incorporate also the first-person point of view through the charts. So, conclusion of this remark, which new mathematics can supersede differential geometry and allow for a non-objectivity of space-time. What does it mean? A deviation from the TPF in the space-time variable. And here you see why it's useful to formulate the measurement problem rather than solving it. In fact, it's a philosophical problem, so we don't care about the solution. I mean, we care, I care a lot, but there is not a unique, universal, definite solution because it's a philosophical problem, and philosophy has never settled any question. Debates are ongoing, and this is why philosophy is interesting. Philosophers just, share something intimate in them, but they don't. Nietzsche has never proved Descartes wrong and whatever. But formulating a problem in an interpretation independent way is super precious. For example, because you can reach conclusions like this, and it might guide the quest for quantum gravity. So yeah.
Is deviation from TPS for the space-time variables?
I don't know. Yeah, maybe 4. If it's clear this way, 4. Yeah.
But your argument might point to an incompatibility between quantum mechanics and GR, but not between QFT and GR, because you address exactly the same system.
No.
You said also that QFT also has the where, etc. So it doesn't show any incompatibility.
Yes, but as also good point. But as I argue here, so 2 things. As I argue here, QFT is full of problems because of this third-person point of view already. So in fact, the 2 remarks could be just one. And QFT works a little bit more than QG because we don't even have QG, but QFT works a little bit more. It's true, but perhaps because, and certainly because it's in the particular case which simplifies everything, where you have no dynamical coupling between space-time and matter. So you're okay, you have a third-person point of view, you have to force your Hilbert space to do something it's not supposed to do, but because you are in a very simple case with a fixed manifold, well, so quantum matter can have this TPF property, but because it's completely decoupled to space-time, well, you can still use differential geometry here because they are decoupled, right? So, but I like your remark. Very good point, and I had never thought about this before. Yeah, a remark here. So the opposite of objective notion of events is a relative notion of events, and there are in quantum foundations more and more thought experiments and subfields tackling this question, especially maybe you heard about indefinite causal orders. It's more and more fashionable, and it's so it was first developed and launched and popularized by Czeslaw Wigner in Vienna, and now everyone in the world is doing that. So it's quite interesting. I don't have time to explain what it is, but it's really trying to put the notion of event and the notion of different causal orders in a quantum superposition, and there have been experiments. The quantum switch is a genuinely realized experiment today. Another branch of quantum foundation studying that is the quantum reference frame approach, but again, I don't have time for that. Okay, this was the last remark of this long sequence of remarks. If anyone has a question, please raise your hand. Otherwise, I go on. So I had the section 4 because remember if you have your notes before, I wrote, is the measurement problem a problem? I could just say, after all, I let go with objectivity, and I say no. We need to care for 2 reasons. One is the quantum to classical transition, and the other is building a metaphysical picture consistent with what we know. I had a section 4 to reply to the first, and so it was entitled "The Emergence of an Objective World." I don't have time, and so next Tuesday we will chat a bit about that. So I skip to section 5, observers. And Wigner's friend. Wigner's friend is a super famous thought experiment in quantum theory, proposed first by Wigner in the 60s, very little studied for a long time, but today, every other day, you have a paper about Wigner's friend released. So, if there is no third person point of view, in quantum mechanics, in fact anywhere, we must introduce the first person ones. This is exactly what quantum reference frames are doing. But now, physics since its advent, I think, has always focused on finding principles that constrain the emitter. So the emitter would be matter in this case, the young part, but never considers the receptor. Here it would be sensations, perceptions, the yin part. So what do I mean? We do physics, so we want to build theories that make prediction of observed events in experiments. Good. So we focused on matter, and we try to say, okay, if matter exists, then necessarily there should be this law, this principle, and we constrain it, and we find the only possible theory that this particle should follow. Good. But there is another strategy. We could just always say, oh, if I am an observer and if I perceive a world, then I should satisfy this and this and this constraint. And this could be very helpful for physics as well. And because maybe you can build a theory of the receptor and find, great theorems and great equations that could turn out to work very well. But the strategy would be completely different from the Young strategy, but it would be physics as far as I write an equation predicting the theories, right? So the lesson of quantum mechanics. Believing that there is an emitter pre-existing to the receptor is the godlike point of view, is the third person point of view, where you have this, you can write down on your paper the full state of affair of the universe. Independently of you, you forget yourself, you disappear in your paper, but it's the third person point of view. And so the lesson of quantum mechanics is that it is not possible. So the lesson of quantum mechanics is the emitter does not pre-exist to the receptor, but they co-emerge backgroundlessly. And so this is an example of backgroundless co-creation. But this is another example of backgroundless co-creation. So right, left. And another example of backgroundless co-creation is this. Long, short. The very notion of right is not even meaningful without the notion of left. It's the same for a receptor and emitter.
But you don't deny any causality.
what's the link with causality? I'm just talking about existence. I'm just saying that the world come into being at the meeting between an emitter and the receptor. Causality is not immediately linked in my mind to this, but if you have a link, I'm curious.
Maybe I'm very naive, but I would say that if you receive something, you have to emit it.
What? Sorry? What?
If you receive something, if I receive a letter, the letter has to be sent
by some
or
no, I don't see it in this way. For me, in fact, I mean, though this is purely personal, purely subjective, but for me, the building blocks of my metaphysics are sensations, and I've so much let go with the very notion of an objective world, that I believe that the world is nothing but the set of sensations perceived by entities. I don't know exactly what is an entity, unfortunately. We will come to this in a moment, but. And you don't have to agree with me to agree with the rest of the course. I'm just saying, replying very subjectively how is my metaphysics. So I believe there is nothing but sensations, and the apparent of an objective world is just a strange intersubjectivity, a strange coincidence of correlation between the perceptions of different entities. So no, I don't believe that if you perceive something, it had to be emitted by something, because this is exactly the view from nowhere attitude.
not sure. Well, that's it. We can debate for a long time.
Yeah, of course, but we will.
No,
Not today.
Otherwise, some people will be
Yes, Kevin.
Can you just comment on what you mean by like a notion related to nowhere?
Sure. That's why I'm not saying what it does. I'm saying what it does not, what is not true. I'm not saying what is true. I'm saying what is not true. What is not correct to say is to talk about an existence of a receptor. Again, this course, just like any philosophy course, is just a sequence of words that cannot be defined individually, but at the end of the course, hopefully, people have still got the message. Good example, yeah. Good. So now, this was just an introduction for explaining what is Wigner's friend thought experiments. And this backgroundless co-emergence. So I could write. Yeah, I will write it. You remember the first session I wrote down what's in one sentence the punchline of what is the challenge of quantum gravity. I think I wrote. Yeah, I wrote building a backgroundless theory for quantum matter, because GR Einstein a century ago managed this incredible feat of building a backgroundless theory for space-time and classical matter. And no one has been able in a century to do the same for quantum matter, so namely a backgroundless co-emergence of space-time and quantum matter. And the reason is the fact that differential geometry is deeply incompatible with the violation of the TPF.
What?
Oops. Yes.
About your work unaware, do you explain something about if you get a signal reads? How to explain if you don't know the origin of that signal? We could just violate the causality principle. What about causality?
So yeah, that was the question. So it's interesting that two persons associate this with causality issues.
Yes, because see, I understand the proposal about background independent theory, but backgroundless is the first time I heard. So in this world with sensations, but without to think about causality, how to but to set this in a quantum gravity theory.
Okay. Okay. So two things about backgroundless. So when I say backgroundless, just understand background independent, but I think this is more accurate. I introduced this word in my PhD thesis because we are not looking for a theory in which is independent of the background. We are looking for a theory in which there is no background. So I think it's more accurate to say this. About causality. Okay. One punchline. Quantum gravity challenge. In one punchline, how to conceive a notion of causality. Well, causality. So yeah, you know, by there is 𝗰𝗵𝗽𝗁 theorem explaining how the full geometry, the full Lorentzian manifold in GR can be entirely recovered if you just remember the causality relationship between the points. You forget everything about the metric, you remember just the causality, and you can recover the metric up to a conformal factor. So intuitively, space-time is just a causality network up to a conformal factor, yeah. So if you want, here I can add plus conformal factor. How to conceive a notion of causality, meaning space-time in the absence of objectivity. This is the second punchline to define quantum gravity in this course, but it doesn't solve anything. I'm sorry, but yeah, I can't today. I can't answer anything better, I'm afraid. So this was just yeah, an aside.
Another thing, I think, could you consider the QG challenge? Or, from my point of view, if you are trying to build a quantum gravity theory consistently, the main problem is about to solve classical questions from Einstein's theory, right? Some point about, think about the first solution, considering the Einstein equation. You have a solution with singularity, but you don't have theorems solving that problem. You have conjectures, like 𝗏𝗏𝗏𝗏, but we don't have solutions. So first of all, we don't know the core of the space and time, considering Planck scales, for instance. Like if you are going to very small lengths, I think it's impossible to understand in a quantum mechanical way the solutions from Einstein's theory. So we are looking for a new theory.
Sure.
Gravity from the classical theory. So many problems, many issues, many situations come from that.
Yeah.
So to build a different proposal, I think you should establish some set of axioms. So the main proposals, considering quantum gravity, we can say like this theory, but we don't know how to reach the unique theory without experiment. But we must we should look at least for this first set of axioms, I think. That's my point of view. What do you think?
No, why not? It's interesting because so many people here, since I arrived in Marseille, told me about quantum logic, which I am quite ignorant in, but I will definitely read more about quantum logic because your question hits at finding the quantum gravity logic in some sense. I guess I agree. However, how will you find the axioms if you do not start with some kind of reflection of this type, like trying to see what is really the core of the problem, the incompatibility, to get some inspiration, and the TPF might probably appear somewhere in your axioms and so on. But I mean, finding this set of axioms, if it's the thing that we have to do, is a very long-term goal. So for now, slowly but carefully, I try to say what I can say. And so yeah, probably it's a good idea, but I don't have this set of axioms.
It's a good idea, but you have to do it.
So this was an aside, but continuing this, and let's introduce Wigner's friend experiments. So introducing the first person point of views is the purpose of Wigner's friend thought experiments, proposed in 1961 in a paper entitled On the Mind-Body Problem. For Wigner, so what's the setup? You have a lab, perfectly isolated, so you can really treat quantum mechanically what's inside as an isolated object. And here you have a, say, a spin 1/2, right, in superposition up plus down. And here you have Wigner's friend, and here you have Wigner. And perfectly isolated. So for Wigner, and what does the friend do? Well, he was established before that the friend will enter the box, will close down everything, and the friend will perform a measurement of the spin in this axis. So for from Wigner perspective, the evolution inside reads, so you have Earth up plus down, tensor friend in a ready state, if you want. I don't write the normalization. I told you again last time. When we work on the measurement problem, we have much better to do than worrying about the normalization. So at first they are non-entangled because the friend is just in a ready state, not coupled. And then evolution, the measurement of the friend takes place, and so now the two systems are entangled. Right? It's not a product state, pure tensor. What? Is F really? It's yeah, we have 0. It's the friend. It's the state of the friend when before the measurement. So the friend doesn't know the outcome and haven't measured yet. And then F up is the friend has seen up. Now, so what is surprising? If Wigner has full quantum control on what happens in the box, typically, suppose Wigner can apply any unitary evolution he wants inside. Like typically, imagine this is the Wigner's quantum computer. He can do really whatever he wishes. Or equivalently, suppose that Wigner can perform any measurement on this joint system. So the Hilbert space describing this joint system is terrible because here it's just a two-dimensional system, Hilbert space, but here it's a huge Hilbert space describing position and momentum and any properties of billions of particles. But suppose Wigner can apply any U to the box, or equivalently can what we call super measure. So this is a very convenient word. Can super measure the system spin plus friend. What does it mean to supermeasure? It means we use this word in the context when an observer measures another observer, but in a non-classical basis, like in a basis which is not made of states of perception. So how to explain that in short? This lives in a very big Hilbert space. So f up and f down are two orthogonal vectors in a super big Hilbert space. But suppose Wigner has full quantum control, he can measure in principle any orthonormal basis. And so he can find an orthonormal basis in which these two states of perception, up and down, are not part of, right? And so he can, and this is we call super measuring. Typically, I can write down an example of basis of question that Wigner can ask, which will count as a super measurement.
So do you have a definition for
super measuring?
about measure? Just simple. If you have measure, you are looking for a super measure, right? But you have this predefinition about measure or not.
So the question of normal measurement, I introduced this in the first lecture, and so I will not explain again. But this.
No, that's not about the standard definition about measure, but here we are using the same definition about measure.
Yeah, I will explain exactly what kind of measurement he can do for the. But I would just wanted to introduce this word of vocabulary, which super measuring means measuring an observer in a non-classical basis, in the shortest definition I can give. But just I will give, if you forget about this, if you want, and just consider the example. For example, he can measure. It's extremely convenient to use this word in when we discuss Wigner's friend. He can measure the basis so up f up plus down f down. This is the first element of the orthonormal basis I write. Second element of an orthonormal basis, and then you complete however you wish. It's easy to check that these two are orthogonal. So I'm really writing an orthogonal basis. So I'm really writing a question that, in principle, Wigner could ask to this quantum system. Of course, in practice, technically speaking, we are not able to perform such measurements, such non-classical measurements. But suppose Wigner could do that. Well, so in this basis, you have the first vector, let's call it psi, is exactly the state of the box itself. So with probability 1, you will get outcome 1. And with probability 0, we'll get anything else. But what does it mean? Yeah. So yeah, indeed, the purpose of the experiment is to probe the presence of a collapse or not. Well, it's an old-fashioned way of saying things, but yeah. The important thing is that if Wigner does that, his statistics will his measurement is in fact an interference experiment between these two potentialities, these two histories. And so by measuring in a complementary basis, you make the two superposed histories interfere. And therefore, you will have the TPF violated. And therefore, you cannot, in Wigner's statistic, you cannot condition on this or this and get a TPF. Wigners will observe a deviation from the TPF when conditioning on the friend's state. Wigner will observe through his statistics a deviation from the TPF because it's an interference experiment. When conditioning on the friends just nothing more complicated than any other experiment of interference experiment we've encountered so far. You have a system in superposition, you measure in some basis, you extract the statistic, you see a violation of the TPF by definition of what is a superposition. But what is weird here? So the weird thing is that both up, friend up, and down, friend down seem to contribute to Wigner's remember for example the remark I made on Schrödinger's cat. It was exactly the same problem. Schrödinger's cat, the mystery is not that the cat is both alive and dead. The mystery is that if you do another measurement, if you can do an interference experiment in which you have a violation of the TPF in the two variables alive and dead, then it's super weird, because it means that both histories, alive or dead, or here friend having seen up or Frank having seen down, both histories seem to have an influence in the observed statistic of Wigner, which is kind of weird because, I mean, Wigner's friend is just like Wigner, right? The friend should experience one and only one thing, and so it's super weird that the other history, the one that presumably did not happen, still contribute to the statistics. So
how is that different from the double slit experiment?
Yes, thank you for this question. It was exactly what I was about to write. What is different? So this is nothing but interference. So why has people written so much about Wigner's friend, and why are people currently writing every day a paper about Wigner's friend? Why are we so how do I uneasy when in this case more than with a qubit or an electron? What is so special when an actual human being, or possibly a cat, is introduced in the game? So if you have any proposal, I take them. Otherwise, I write my proposal of answer, but yes, so the super measurement, yes.
Yeah, another basis. In the basis of his friend this time, not in the weird basis he would make.
Ah, sorry, can you repeat the question then?
In order to do the conditioning on the friend state, you would have to measure the friend state.
No, because it was agreed from before that the friend, so Wigner knew that the spin was prepared in a 1/2 superposition, and it was agreed from the start that the friend inside the box will measure in the corresponding basis. So Wigner knew that this is the state inside, and this Wigner knows this for sure and doesn't have to measure the friend before, because it was agreed from before, and Wigner knows what's the unitary. So this is the good object that encodes all the predictions that Wigner can do about any measurement he can perform on the box. But the mystery is that when he performs, for example, this kind of super measurement, then it seems that both potentiality contribute to the statistic. What is different? What is so special when you plug a real human being in superposition? Why are we so annoyed with this idea of humans or maybe cats? Why did Schrödinger wrote this example about Schrödinger's cat, and not, why do we not talk about Schrödinger's electron, right? What is weird when it's a cat? So I claim that this is the core tension. There is a conflict between, on one side, the multiplicity of potentialities all interfering, and therefore all contributing to the statistics, versus the unicity of the subjective experience. And I think, so this is exactly the reason why Wigner's friend has been studied so much, and it's the very motivation for Wigner, even though he was not, explaining it this way probably, but the reason for Wigner to present things this way. And so the measurement problem is even more severe on observers. And now, for once, I can give a definition of this word. I define observers precisely in such a way that I capture this tension. But it will be a philosophical and not a mathematical definition. I think you now understand that we are not doing a math course. System equal system granted with subjectivity. So whenever you read a word in the Quantum Foundation literature, the word observers, and you find it literally everywhere, I propose to understand it this way. But really, believe me, it's far from being a consensus, because no one agrees on the definition of this word. We struggle so much, and it's a part of the measurement problem to struggle with this notion. And this is also, again, a motivation for quantum reference frame and so on, trying to introduce the first person point of view and so on. But everyone struggles, and I propose this definition. Why do I propose it? Because I think this captures the biggest conflict of the measurement problem, which, when applied to observers, is even more strange. And this is a current hot debate. So current hot debate. So which system are observers? Current hot debate in Quantum Foundation. Literally everyone, not everyone, more and more people are trying to solve this question in a way or another. So 2 examples of papers I can recommend. So there is this paper, so by Bruckner, 2021 entitled "Qubits are not observers," with a very simple argument, which, I mean, everyone had thought about it. It's not a revolution, but it had to be written down at some point. It's not even published. It's on the archive, but really I can recommend. It's very simple argument for why qubits cannot be observers, because they don't have enough distinguishable states of perception to be a consistent observer.
But does Bohmian use the same definition of observer that yours?
So most of the time, this word is undefined. Is undefined. So you can have a look at the paper. I'm not even sure. Maybe it's yeah, there is a tentative to define it in the paper. I don't exactly know, but the argument is just, if it was a consistent observers, it could record, at least it should be able to observe another qubit, at least, because it's the tiniest, the smallest other quantum system, and so it should be able to record at least, to have at least 4 states of perception distinguishable, namely orthogonal, because there should be a state where the qubit has seen up, the state where the qubit has seen down, yes, but in the Z basis, but you should also be able to be an observer who has observed in the Y basis and down in the, so at least 4, and in fact much more. Yes. Yeah. So as I told before, I confessed that my metaphysic, my building block for my metaphysic is the notion of sensation. So since it's my most primary notion, I will struggle to give you a definition, but maybe, so I hesitate a lot between subjective experience or sentience, or of course consciousness, but everyone tells me, oh, why not consciousness here? So for me, it's different. Consciousness and subjectivity is different. So many people are surprised when I say so, and they would like to equate the two words. But for me, it's very different. I feel every day, but there are very strong variation of my level of consciousness from a day to another. Personally, I don't know if you experience the same, but I mean, this is how I want to use the word consciousness, and so. But I feel every day. Yeah. So I am I have subjective experience for sure all the time. Consciousness, I don't know what it is exactly. Subjective experience is so primary that, yes, I see what it is. I cannot tell you what it is, but I see it. Maybe you could use the word qualia, very fashionable in philosophy of mind. Qualia, yeah, what it is like to see the color red, or to be a spider, or
But there's strong reason that any experience must be unique, no superposition, because it forces this concept to be reciprocal.
Yeah. Have you ever experienced 2 outcomes? Yeah. But I'm not saying quantum particles are observers. I'm saying when I plug my friend, and I believe my friend is just like me, so my friend should have unique experience just like me because it's a human being, or my cat. Well, then it's weird if there is this tension. For a qubit, I don't know. Maybe for a qubit, the measurement problem is not so painful. That's why the measurement problem is severe on observers. But I don't know which are the observers. But for sure, for sure you are an observer, I believe so. And for sure, if I can place you in superposition, it's uneasy for me to make sense of this. But for an electron, it's less shocking.
But I can be in
For sure. What do you mean? It depends on which basis, because you are very superposed in most bases, except the classical basis. Yeah, so you are not superposed in something like a coarse graining of the X and P basis. You are very superposed in most complementary bases, right? Yeah. Coherence is a basis-dependent notion. You can be not superposed. For example, if you are a qubit in state up along axis Z, you are not superposed, but in the other bases, you have a lot of coherence. Yes, I can tell you a lot about that afterwards, because I have worked a lot on measures of coherence and how they depend on the basis. I gave a talk in LIS in January about that.
Not so much overlap to say that there is coherence, but my the basis in which I am.
So in the classical coarse-grained classical basis, you are not so superposed thanks to decoherence. True, but the purpose of isolating the friend in a perfectly isolated lab is to get rid of decoherence, or to be able to apply any unitary. It's also because of course if you open a single hole here, everything decoheres immediately, and Wigner cannot detect any violation of the TPF. Unless the measurement goes super fast and is faster than decoherence, because this super measurement would be enough. But anyway, is it okay? Do you? Yeah. Okay. Another example. So, who or what are you friendly with? This is a quite famous already question asked by 𝗰𝗵𝗽𝗁 and collaborator. And so it's the context of the local friendliness theorem that we will study next time. But what are you friendly with? The meaning of this question asked by 𝗰𝗁 is exactly which system do you grant? So I don't exactly know the term they use, but in my own term, which system do you grant with subjectivity? Which system can you place inside this box and say it's weird with respect to the local friendliness theorem that we will study? Okay. So it's almost time. Therefore, unfortunately, I will not have time to go through the 6 interpretations. So I will just the introduction of the.
But are you going to postpone the 6 interpretation next time?
So we can discuss. Yeah, we can discuss that. Either next time I do the 6 interpretation, but it means that then I will have talked for 3 sessions about the measurement problem. I will not complain about this because it's one of my favorite topics, but it was entitled Introduction to Quantum Foundations, so it would be great also to introduce to Bell theorem and other no-go theorem, because it's also extremely interesting, and in this way you will be able to see how the TPF can be used in many other contexts. But if you really want to see the 6 interpretation, maybe I can do it next time. But yeah. Okay. Good. So 6 main interpretation. I just write the introduction and then we stop. 6. Okay. So perhaps we can do 1. If you want to, we can make a poll, and if you vote, we can do 1. I don't know, but just first a few words. So this year, a recent Nature survey. So recent survey in Nature. So for the reference,
there is 1 vote for the chat. Antoine
wants the interpretations.
No?
Oh yeah, no, yeah, I knew that. Yeah. Maybe if no one else votes. So 𝗬𝗍𝗍 2025, entitled "What does quantum mechanics say about reality?" So you can check this survey because it's not technical. It's really supposed to be readable by everyone, but in fact it follows loads of previous similar surveys. So Schlossauer, Koffler, and Seilinger in 2013. another one in 2016, 𝗬𝗂𝗺𝗺 and Nielsen, etc. So each of these surveys arrive at the same conclusion, more or less, showing how divided the community is on any interpretational question you can think of. That's why it's a challenge to give a course about that, because I mean, if I had pretended to be objective, then it would be, of course, a failure. So I don't even try. Interpretational question. Any question you can think of about interpretation divides almost like if you have 5 possible answers, you get 20%, 20%, 20%. I'm a bit joking, but not that much. First, let's define what is an interpretation. What is an interpretation? An interpretation is a metaphysical picture that you build to account for the deviation of the TPF in our world. Is that accounts for the violation of the TPF. And they all manage in some sense. I'm not saying some interpretation fail and others succeed. So in some sense, they all manage, but they raise in turn new difficulties specific to anyone, to each of them. So they raise in turn some new specific difficulties, which can be seen as their own measurement problems specific to each of them. But I do not even dare to write this because sometimes the problems are so different conceptually. So, but importantly, I just want to stress that none of these 6 interpretations is stupid. They are all very interesting. If they have survived so many years of such an intense and quite violent debate, for sure they cannot be stupid, right? So, but in the community, it's very frequent to just meet people who are just despising everyone else and trying to identify their allies and their enemies, and saying that anyone thinking differently than me is stupid. But really, there is something to learn from every interpretation. So I will finish with that, I think. This is a timeline. A timeline so that you can have in mind when did they appear first. Copenhagen interpretation, 1928. I mean, yeah, it's schematic, it's just to give a date. This is Bohr, one of Bohr's very influential paper. 1962, 52. So this I wrote it again already. This is Bohmian mechanics. So in fact, one of the oldest interpretation we have. A little after 1957. Thierry, do you have it? Yeah, many words. Everett, many words. 1986. Well, there were some pioneer works before that, but really the first proposal of no collapse models. So the GRW. Yeah, the first session. Remember, we were proving the no communication theorem, saying that you cannot convey information through a pair of entangled particles. And I said, you know, the first convincing proof was by Girardi, Rimini, and Weber. Well, these three guys also developed the very first collapse model, exactly the same guys, 1986, their paper. And we still don't have much better. We have only two models for collapse model because it's very constrained. So sorry, 1996. This is Rovelli's relational quantum mechanics. Yeah, RQM for relational quantum mechanics. And the youngest one, but it's not a baby because it's already well developed and extremely underrated interpretation, super interesting. QBism. Very, very hard to dismiss. QBism for quantum Bayesianism. But it's a pun with QBist because it's a very phenomenologist view where the first person perspective is primary. And so the world is just the collection of first person perspectives. And the probabilities of quantum theory are understood in a Bayesianist meaning, because you know there are two ways of understanding of philosophically there are two different ways for the foundations of probability theory, right? So one is founding the probabilities as relative frequencies. The other is Bayesianism, and you can derive Kolmogorov axiom from just consideration on lotteries and how much are you ready to bet on something or something. So a probability only denotes your credence in some event or another, but only by self-consistency you can derive all probability theory, so the Kolmogorov axiom and so on.
So you mean that you have an interpretation of quantum mechanics where you dismiss frequencies?
They are purely Bayesianist because in QBism there is no objective world at all. So psi is just a first-person object used by an agent to engage with the world and to describe the most reasonable way to assign credences to what may happen or not. That's all. You're not saying it describes something that is there in a sense, but I mean, RQM is also very, very far from any notion of objective world, super far from that. So it's also in RQM also rational. So Rovelli's interpretation. In RQM you have the quantum state is mostly epistemic, just an epistemic object used by an agent. So I don't have time to go through all of them, but just so I will not have time to do many words or so, but I will give you some names of important names for each of them, so that you know who developed which interpretation. So Copenhagen. So of course Bohr, the main advocates, Bohr and Heisenberg. This was for the pioneers. Much more recently, I mean today, who are the neo-Copenhagists? So Bruckner is probably one of the most famous. There is also Jeffrey Bubb, Michael Cufaro, Asher Pierce. So from this book I recommend, and you can have a look at it. Is everywhere you find Copenhagish punchlines everywhere in this book. For example, one of them is unperformed experiments have no results. This is super Copenhagen. Or one of them is, I like it, it's quantum theory can describe anything, but it cannot include everything. This is very Copenhagen. Bohmian mechanics. So, of course, David Bohm, but before that there was 𝗬𝗿, but he was not fully fledged. Bohm. And who was the most famous Bohmian? Yeah, Bell. Yeah, John Bell. Bell. And today, today Goldstein, Dürr. Yes. Now, who collapse models? No, many words. So many words. It's easy for the first one. Everett, yes. But importantly, yeah. So a name. No, but maybe he's not only a cosmologist, but probably he's also a cosmologist. But David, because David, he was a cosmologist, probably theoretical physicist, but he popularized Everett's idea, because Everett developed many words in his PhD thesis in 1957, but in fact, he was almost unnoticed until, so under the supervision of Wheeler, I think, but he was almost unnoticed until David in the 70s said, that's nice, let's popularize this idea. And because he was David, everyone came to know it and embrace it. Weidmann, today, Lev Weidmann from the Israel school. So Weidmann was the PhD student of Aharonov, I think. Aharonov, Albert. And for the philosophers, so Wallace, probably one of the most famous, Barrett. So this is the Oxford school, not Wallace, but Barrett and Saunders, yes. Oxford school, very active for philosophy of many words. The next one, Colors models. So Colors models, but it's easy. I told you, GRW. So Girardi, the pioneer, and today maybe the greatest name is Andrea Bassi or something like that in Italy, and the Italian are probably it's a hub for collapse model advocates. RQM, so very interesting. I promise I tried to find a single other name that already I couldn't find a single other name. Important figure. So it doesn't mean it's a bad interpretation. It's in fact among my favorite ones. But it's very surprising that, of course, there are some people publishing about RQM, but either it's for criticizing it or when it's for advocating it. I was never comfortable with presenting this person as a an important name of the interpretation. So that's quite significant, I'd say.
May I add some people there, because we have Stephen Adler, Niles, Joshi.
Joshi, no. Joshi is in the collapse models. No. Yes. And the two first one, who?
Stephen Adler.
Adler.
Yes, Nicolas Gisin.
Is Gisin really an RQM guy?
Yeah, I know, but that first paper, the 1984, about the super signaling.
I know, but 1984 was before the very creation of RQM.
Yes,
No.
This nice paper about.
Okay, no, but okay, but I could do that for every other. But I mean, Gisin is definitely not a big name of RQM. Like he's not associated with that, and he's not a proponent of it today, an active one. I'm not even sure he's convinced that SQM is the best interpretation. Do you think so? I'm not even sure. Maybe yes. And Adler, I don't know. Maybe Adler. So if you say ADLER.
Yes.
Okay. I don't know. Maybe.
I think he published a lot of
state vector reduction, something like trying to generalize the collapse model for relativistic theories, for instance.
Okay, so that's not RQM. That's more.
No, it's not RQM. It's collapse model.
Ah, for collapse models.
Yes,
Ah, okay.
I'm talking about
Ah, right. Ah, Joshi, okay.
Yes, Joshi is
Joshi. Yeah. Well, okay, maybe she's some. Yeah. Okay. Why not? Okay. Adler. Yeah. Okay. Why not? Okay, right. And QBism. So the founder, Fuchs, Mermin, other important name, and Jacques Quiénard, who used to be a postdoc in my group, but before me. And so, okay, thank you. I stop here for today.